If you've read your subject guide, you've probably covered this thing called the central limit theorem, but having read it, you may still be a little unclear as to what it all means. So this brief recording here is just to reiterate what is going on in terms of the central limit theorem. And this will lead on nicely into the idea of statistical inference, which we'll be coming to in the next couple of chapters. Basically, we have the following. Typically, we want to do some empirical investigation into some variable. And typically, there will be some population, which is usually very, very big. And to be completely accurate, I would need information on every individual or entity, whatever sort of things we're looking at, in the population. So if I was looking at the population of a particular country, this would typically be many millions of people. But due to resource constraints in terms of time and money, usually it's not very feasible to obtain data on every single person in the population. Doing that would require taking a census, which would cost a lot of money to do, and typically there might be certain non-sampling errors which might creep in. Do refer to your sampling chapter to look into various advantages and disadvantages to these various techniques. So instead of looking at data on the entire population, we will consider a subset of the population, i.e. a particular random sample which we're going to take. So let's say that's denoted by this area here. So this small circle represents a subset of the entire population, and so we obtain data purely on the members or the elements in our sample. Now, from our sample we can compute various statistics, and a very common one to compute is the sample mean, namely x bar, where just to remind ourselves, the sample mean is just the sum of the individual observations divided by the total number of observations n. Okay, so what's all the central limit theorem about? Well, the population distribution may or may not be normal, and that's really the whole crux of this CLT argument. If I'm sampling from a population which does have a normal distribution, then we know the following. The sample mean x bar has a normal distribution with mean mu and variance sigma squared upon n. So this is the case when the population is normal, which is great. However, there's no guarantee that our population will have a normal distribution. But what the central limit theorem says that even if it doesn't have a normal distribution, if our sample size is large enough, so typically our sample here will have some sample size n. So if n is large enough, then even though the population does not have a normal distribution, we can say that x bar has an approximate normal distribution with mean mu and variance sigma squared upon n. So this will be the case if the population is not normal, okay, but n is large enough. Now you're probably going to ask me, well, how big is large enough? Well, this is quite a subjective the answer is going to be subjective to this question. There's no definitive value of what constitutes a large or a small sample. Some textbooks usually cite the number 30 as representing a large sample. However, essentially the bigger the better. So other things being equal, the larger the sample size that you can obtain, the better. If we say that 30 is our benchmark, then do we really mean that if we had a sample of size 29 that suddenly we've got a very, very small sample? Not necessarily. So the point is that x bar, the sample mean, which is a very useful and commonly used statistic. Okay, remember, a statistic is just some function of our sample data. That x bar can be assumed to have a normal distribution regardless of whether we're drawing from a population which has a normal or a non-normal distribution. Okay, in the non-normal case, the only condition that we require is that our sample size is this large enough, however you wish to interpret that. And so, using this approximating normal distribution, we can say the following. Remember, the New Cambridge Statistical Tables, Table 4, gives us cumulative probabilities for the standard normal distribution. And typically, in order to use those, we have to apply the standardization technique. So I can apply my standardization to x bar and say that the probability that x bar minus mu divided by not the standard deviation but this thing called the standard error, remember, which is just the square root of the variance of the distribution. Okay, so for my random variable here, x bar, what is the variance? The variance is this whole sigma squared over m. So if I divide by the square root of the variance, this is the same as dividing by sigma divided by root n. So the probability that this thing is less than or equal to some particular value, in terms of table 4 of your new Cambridge Statistical, we'll just denote this by little x, is that this thing tends to the phi of x as n tends to infinity. So n, remember, is my sample size. So as my sample size gets bigger and bigger and bigger, it means that we can, this normal approximation becomes better and better. But for our purposes, in say statistics 1, really, if n typically is 30 or more, then we can say that this approximation holds really well. Of course, you could apply this normal approximation to a very small sample size, but it just means the approximation will not be as accurate, okay? Because the accuracy of this approximation improves as I increase my sample size. So hopefully this brief recording has just reiterated and made things a bit clearer with regards to this central limit theorem.